Kia ora Year 12 and Year 13. I'm going to start trying to YouTube most of what we're doing in class, and I wanted to start with the really hard starter questions today that were from the 2020 paper. So I'm going to do these one question at a time per video. I'm also going to put word solutions up, but I think at this stage you're probably going to get more out of it if you can listen to why I'm doing what I'm doing. So these questions feel hard because we're suddenly starting to link up all of the complex numbers individual skills that we've learned. And this is one which is a merit question, and we're given, it's kind of a classic setup. We've got a cubic equation here, and one of the roots is, one of the solutions is this, z is equal to 3 plus I, and we have to find the other solutions, and then we have to find the value of b. So there are two ways to do this question. I'd like you to watch both ways. The first way is the more efficient of the two methods. The second one is really messy, but it might be a useful strategy with some other problems. So what do I know about my cubic? Well, we know that b is a real number, and we have to find b, and we have to find the other solutions. So there will be 3 solutions by the fundamental theorem of algebra. We're looking for 3 solutions. Right, we're looking for 3 solutions because this is of order 3. And the coefficients are real, not complex. We're told that b is a real number. So by the conjugate root theorem, we know that 3 minus I is another solution. What we're looking to do is to factorize this out fully so that I can get the third root. If 3 plus I is a solution, we can get a quadratic term in here. So we know that 3 plus I is a solution and that 3 minus I is a solution. And then we're going to have this one here, which will make it equal to 0. And we can see already that this is going to have to be 2z blah, blah, blah. The strategy here is going to be to work with that, clean that up, and then do matching, or we could do long division if we wanted, to figure this out, and along the way we're going to find b, right? But the first step here is to expand this out. Now when I do this, I regroup like this. We've done this quite a few times back when we were doing the conjugate root theorem. That gives me z minus 3 squared, those two. Now next I have minus I times that, and then plus I times that. So they go, which is why the conjugate root theorem is so cool and it all works. And then I have minus I squared, which is plus 1. Expanding this term gives me z squared minus 6z plus 10. Okay, so that's the first bit of the problem solved. Now I'm going to chuck that back into my expanded form cubic, giving me 2z cubed minus 15z squared plus bz minus 30 is equal to z squared minus 6z plus 10 times something else. Now there are different ways to do this, but you might just want to put a little box, so 2z plus box, or you could call it k or whatever. And in this case it's really easy to see what I must have to get that negative 30. So the box is equal to negative 3, and we can put that in there. Now what I've got, I'll just turn off the ink to shape, sorry about that, is this 2z cubed minus 15z squared plus bz minus 30 is equal to z squared minus 6z plus 10 times 2z minus 3. Now I matched it on this, but I can now check it on the other coefficient. So we see if we expand this, we're going to get 2z cubed, and then I'm going to get minus 12z squared plus 20z minus 3z squared. So that's matching up to that, which is a good thing. Where was I? Minus 3z squared. Let's just get rid of those. Plus 18z minus 30. That gives me 2z cubed minus 15z squared plus 38z minus 30. And look back at what we needed to find. We had to find b. So b is equal to 38. Sorry about the noise, guys. B is 38. And the two roots are, the other two roots, my conjugate root, which was 3 minus I. And from in here, z is equal to, brain going very slowly, z is equal to 3 over 2. Right? Please don't stop watching the video yet. I want to show you this other way. So that's the first method. The other thing we could do here doesn't use factorizing, and it, in this case, doesn't even use the conjugate root theorem. It uses the fact that if something is a root of a polynomial, that means that it must make this a true statement. So what I can do with this is substitute in 3 plus I, and I'm going to get a q2c thing to expand, but then we can figure out b that way. But then we still have to factorize, and we end up getting b. So I'm going to do this method. Please watch it, because it may come in handy in another yucky question. We're starting out with 2z cubed minus 15z squared plus b times 3 plus I minus 30 equals 0. Now my strategy here will be to match up the real bits and the imaginary bits. So a really useful thing to think about is that when we're working in the complex plane, 0 is equal to 0 plus 0i. So the strategy here is to sub in 3 plus I. I've already half done that. I really am half asleep. Right, let's just back up a step. So there's my equation there, right? So 2z cubed minus 15z squared plus bz. And that has to equal this. Now I'm going to substitute this in wherever I see z. Okay, so 2 times 3 plus I cubed minus 15 times 3 plus I squared plus b times 3 plus I minus 30 is equal to 0 plus 0i. So let's expand, and I'm going to do that because I'm making this for 13 MCA. I'm going to do that using a binomial expansion on that pretty quickly. So 3 cubed 27 plus 3 squared I times 3, that's my Pascal's triangle number, plus 3i squared times 3, that's my Pascal's triangle number, plus I cubed minus 15 times, expanding this, 9 plus 6i plus I squared, plus 3b plus bi minus 30. And that equals 0 plus 0i. So lots of places to screw up the just simple calculations. So let's go slowly here. We get 54 plus 54i plus 2 times 9 plus 18i squared, just leave it like that for now, plus 2i cubed minus, now in here, 9 plus I squared is 9 minus 1, which is 8. 8 15s are 120. So minus 120 minus 90i plus 3b plus bi minus 30 equals 0 plus 0i. So thank goodness we've done all the gross stuff. Cleaning that up now to find the real part, 54 minus 18 minus 120 plus 3b minus 30 is equal to the real part here, which is 0. Okay, get your calculator if you're feeling tired, because it would be a shame to stuff this up at this point, right? So 54 minus 18 gives me, I'm thinking, 36. 36 minus 150 gives me negative 114 plus 3b equals 0. Now, we know from the first part that we should be getting 38, and luckily we are. So 3b is 114, b is equal to 38. I really hope you can see that that is a method to be used in desperate situations only. The second thing that I'm going to do is I'm going to show you that it doesn't matter if we do that using the imaginary part, and the numbers work out very slightly nicer here because we've got b times I, so we don't have to divide. Right, so the complex bit, what have I got? Well, I've got 54i minus 2i, because in here I squared is negative 1, minus 2i. So I'm just doing the coefficients here. 54 minus 2 minus 90 plus b is equal to 0. And that gives me directly negative 38 plus b is equal to 0. B equals 38. But look, the trouble with this way is that I still have to go back now and get that third root. So there really is no way around using the conjugate root theorem in here, except what I'm doing is that I can now put b back in there so I can see more easily what it is that I have to factorize. But we still get here z minus 3 plus I, z minus 3 minus I, and then 2z something something. And we end up having to do all of that expansion anyway. The difference is that we're not hunting for bz, we're hunting for 38z. Okay, I know that was 11 minutes long already, but that's partly because there are 5 of you away probably for a wee while, and I'm not going to go through this in class now that I've videoed it for you. I'm going to slowly work my way through the other 4 questions this evening, and let me know if you've got any questions when you've finished watching.